So hello, welcome to NCSA's Center for AI Innovation training dedicated to the use of machine learning. Today I am very happy to introduce my colleague, NCSA data scientist or data engineer, Aaron Saxton, who is going to talk about how to get started with machine learning using our HAL system as a platform for this. So Aaron, please take it from here.
Great. Thank you very much. Right, so today we're going to learn a little bit about neural networks, some convolutions, convolutional neural networks, and sort of what to expect when you run these things, and most importantly, how these things are executed and used on HAL. So I guess, first things first. Let's get you logged on. So the first thing to do is you're going to want to get onto HAL Open On Demand. Oh, okay, you can do that. Okay. And maybe I will post this on the chat so you can just go ahead and bring this up. Just click on it and get there and copy and paste it over. Which will bring you here. And you're going to want to start a job. So Job Composer.
So try to go to Interactive Applications menu instead. So something, it looks like something is happening there.
Okay, let's stop this. Let's start again here. Oh, here we go. Is this the usual, we're servicing a whole bunch of people crunch?
Yeah, I wonder, this is taking longer than expected.
Okay. Let me, when in doubt, try a different browser. So here I have my Firefox. My credentials might be stale. I've been going over this past day or so. Don't save. Oh, I have my notifications off, so Duo. Oops. Approve. Uh-oh. So one person said it's working quick with them. Ahmed, are you on campus, or are you at home on an ISP?
I'm using my own Wi-Fi, home Wi-Fi, but first I logged in using the terminal.
Okay, so, well, I'm kind of waiting for this. So ultimately, whoops, there it is. Ultimately, you want to get your notebook job going. And so I already have one going. Hopefully we can just short circuit, and I'll bring that up in a second. But in the meantime, I put together, so I used a previous presenter's work and had to update some of the details for whatever latest versions are out here. But we put together a couple of IPython notebooks. So you're going to want to clone this repository onto into your home directory on HAL. So I'm going to go ahead and paste the Git address there on our Zoom chat. For more information, you can go to the Git repo at that link. to kind of browse, and if there's anything, maybe you didn't like the SSH link and wanted the HTTPS, we're not going to do anything today that will matter one way or the other. So go ahead and copy our link, bring up the terminal. You'll have to log SSH onto HAL. Go ahead and copy this into the chat so you can get that address quickly. It turns out I had authenticated myself earlier. You'll have to go through whatever your process is. Once you're on the login node, the way I like to keep my stuff organized is I have a demo directory. You could do it directly on your home directory. One way or another, it won't matter. And we do git clone and paste the git address. That's basically everything we really need to do on the command line for today. Is just get that git repo into your home directory. You can take a look at it. This is what's in it. So cool. Any questions? Okay, I would like to walk through how to do this process with you, but since things are kind of laggy at the moment, I'm going. If you have questions about how to actually start up your Git notebook, we have some help here on the call that you can message your questions onto chat, and they'll help you get this notebook running. So I'm going to go ahead and connect to my particular Jupyter notebook, and it launches me and dumps me into my home directory. So, right, all these directories here are what you see here. I put my the clone of the Git repo under demo, and then HAL CNN tutorial. So today we're going to start with, well, intro. Go ahead and launch that. Okay. Do we have any questions on that process so far? So the goal here is to get you guys looking at your own version of this intro here, so you can go through with it and kind of monkey around with the numbers and fiddle and learn and explore.
And by the way, so in order to run these notebooks, do you need a GPU or do you need a CPU version only?
All the testing I did was CPU only. Okay. However, everything we don't go into too much that's CPU specific. Everything we talk about has a GPU specific. Everything we talk about has a GPU analog. It's just beyond the scope of these of this particular lecture to go into that.
And so one doesn't know when you are starting the notebook, you need to specify this as a train for the reservation HAL_ training. This will give you a working session, because otherwise the system is too busy to. So can you maybe you can try it now if you go to interactive sessions.
All right. No. Okay. Things are going well. Good. So let's roll back a little bit. If you're trying to get a Jupyter notebook up, the landing page is this guy here, interactive Jupyter notebook. I'm pretty sure Jupyter Lab will work too. I was just doing all my testing in Jupyter Notebook. We want a CPU partition. Last time I chose 3 node hours just so I could grab a job before all of you showed up. 2 hours will work for you guys. Oops, did it work? So this one, nope. And then name of reservation training. Turns out the minimum number of CPUs is 4. I recommend that you use that. No GPUs. And then go ahead and click launch. I guess I'll start it just so you can see that it happens, and I'll nuke it once it brings me over there. So great. Then you'll get this little blue titled section here. It says it's starting. It'll take a few moments, depending on how many of you guys are. Oh, that started really quick. Then you go ahead and click connect to Jupyter, just like I did before. And that will pop you over to this screen. Go grab the intro Python notebook or Jupyter notebook. And this is where our story is going to start. You know, the world of machine learning and AI has gotten pretty robust lately. There are lots of exotic and crazy things going on these days. You know, the latest and greatest is Stable Diffusion and all the AI generated artwork going on out there. But even with all of that crazy things going on, everything does boil down to a couple of key core concepts going on, and the smallest the smallest concepts here aren't that insurmountable. So that's where we're going to start. We'll start with some linear regression and gradient methods for fitting them. There are other methods, but gradient methods are the ones that are extended to more general models. We'll talk about neural networks, convolutions, and also something called max pooling. We'll also get into loss and error functions. So neural networks were, by their namesake, inspired by neurons. That by itself isn't super insightful, but let's look at the anatomy of a neuron briefly. Right here on the left side, we have its nucleus and all its dendrites. In particular, what's happening is on the left side, we're getting lots of different, the neuron cell is getting lots of different inputs. Exactly how they're connected, there's a whole bunch of biology going on with that. There's a whole bunch of biology going on with that, but we simplify that as simply a weighted sum. So on the right-hand side, this is the formula equivalent that we're mimicking in software. So all those inputs somehow get combined, and then the combination gets processed, and it passes that signal off onto another neuron somewhere else. And so again, that formula winds up being a sum across a whole bunch of its inputs, these xi's, times some weight plus a bias. So this is where we'll start. This looks ridiculously like a linear function. It is indeed a linear function. So that's where we'll start, is with a linear regression. Okay, so one detail I forgot to bring up. It won't matter on this this notebook, but which kernel you're using is going to be very important. Sometimes it pops up with the correct default kernel, sometimes it doesn't. So to be safe, we come over here, we go to change kernel. We want to use the one at the bottom. So Conda env wmlce version 1.7.0. All right. So here we go, moving our way through the IPython notebook. Let's just get some of this running here. Okay, so there it goes. So for this cute little toy problem, we're going to generate some synthetic data set. We use NumPy array to build some samples in our domain, the input, the X, and we create a formula for the output, just a simple 2 times X. Now, to make it look a little more like quote unquote real data, we're going to add some noise to that. And plotting this comes up as this plot down here. Most importantly, the mental model you should be building here is that real world data is indeed noisy, right? There's no real measurement you will ever make that falls exactly on a line or on something very a specific function. So that's what we're emulating here, is real data is scattered all over the place. But we want to try to fit a model, a very precise object, to this data. In particular, a linear function. Now, this function is parameterized by two values. There you go. M, the slope, and as from college algebra, you learned that as the slope, and B, the y-intercept. So what's significant about this is, we've decided what data to choose, and we've decided what function to choose. The thing that's unknown here is not the data. The data is clearly scattered in front of us. It's not the function. We have the formula of the function right in front of us, but it's the parameters in the function, the M and the B. Our goal is to find specific values of M and B so that we have a model that closely represents whatever this scatter is here. So we write down a function that describes how to measure our model against data. And we use something called well, there's no root here, but root means square. So in this formula, we take the outputs of our model, the y twiddle sub k, and we take the actual values from our training set, our data set, and we simply subtract them. We see how close is our model to whatever the real world data is. And of course, we square that. There are other formulas you can put in here, but there's some nice reasons to use a square. And we sum that across all our samples. So this is adding up how bad our model is matching the data. There's a normalizing factor out here too. So this formula here is measuring how bad our model is representing the data. We want to minimize that. We want to make sure that our model is indeed a good representation. The run-of-the-mill technique to do that is something called gradient descent. From multivariable calculus, you probably have learned that that we can take a derivative of this formula with respect to parameters. The parameters we're taking the derivatives with respect to, indeed, are the parameters that parameterize our model, our linear model, the M and B. And the amazing result from, from calculus is that when we take the derivative with respect to m and then also the derivative with respect to b, we're getting two things out. That's a two-dimensional vector. And the amazing result from calculus is that vector points in the direction of steepest descent. So whenever people are throwing around the buzzword about gradients and gradient descent and all that, that's what they're talking about. Is they're measuring what direction in the parameter space do we need to go to improve our model? That's what the gradient points in. That's what the gradient does for us. And so the nomenclature is down here. The partial derivative with respect to, or the derivative with respect to m times a constant. The derivative of the loss with respect to b times a constant. And this is the way, this constant is what we call the learning rate. And this is the way we update our parameter. We move it forward a little bit. This particular loss function is nice, simple, nice and sweet, combined with our formula here, because the derivative of this is just you pop down your 2 from your exponent. Okay, so blah, blah, blah. I need to speed this up. This is just the introduction stuff. So algorithmically, the code that actually goes through and does this process is this cell here. So we initialize our a guess of what m should be and what b should be. We're just going to take a random guess. That random guess, we apply our formula, and this is what the prediction is. And so down here, this is our same scatter from up here, but now we've plotted our initial guess of what that line is. It is horrible. Not terribly surprised. We chose random m's and b's. Now in the next cell, we actually go through the process of actually, I'm going to do something here. Let's do one step of this thing. Oh, oh, yeah, good. So I just did this process of computing the gradient, multiplying times the learning rate, updating the parameter, and putting the parameter back in once. And the loss is something big. All right, let's do it again. See if this breaks. Let's do it a whole bunch of times. All right, so after we go through that process a whole bunch of times, we went from a loss of, what was that, 12,000 down to a loss of 1,000. Whether that's good or bad, it's less. Let's plot that. See. I mean, I guess it's already kind of here. And indeed, computing the gradient, updating. Multiplying it by a learning rate, updating your parameter or modifying your parameter and updating it causes this red line to match our scatter. Hooray. All of machine learning and AI uses some variation of this process. We will talk about another one, a modification on this process called RMS prop later, but this is the mental model. Some things I want to, no, I'll say that later. Okay. All right, so that was a linear regression, but we want to do something fancier than a linear regression. There's, of all the data sets that you can choose out in nature, there are plenty of things you can do to make them linear. And in fact, the more classical studies, that's what it all boils down to: is how do you measure the thing, find the region, take the log, so that your problem is linear. But we've, the last 20 years, 30 years, we've discovered that we can actually get a lot of traction by considering much more complicated models. And the thing I glossed over when I introduced the neuron up here is, yes, the first part of the neuron is just a linear regression, is just linear. But the thing that separates this is applying a nonlinear activation function to that. And that's what advances us past just a simple linear regression into a neural network. And so when we have a neural network, we decide, let's see. When we have a neural network, we decide how many inputs are going to be in this neural network. In our previous example, we only had one. Right, we just had, wherever it was, this guy here. But abstractly, we want to analyze data that has a lot more inputs, images, for example. And so every cell of the input needs a weight. Needs a weight to be associated with it. What was a slope needs some weight to be attached to it. But the formula for a neural network involves a lot more than just a single weight. Indeed, you can choose however many hidden layers or how many hidden neurons you want. And so what was just a simple slope from the linear regression is now a big matrix comparing every input to every hidden unit. And it's that matrix that we need to discover what the optimal values are to fit a classification. So we have our weight matrix, we have our bias vector. If we have a high dimensional piece of input, stretch it out into a vector, perform matrix vector multiplication and bias addition, and this outputs gives you an output layer. And the way we interpret this output layer is we usually look at the greatest value is what the prediction is. Okay, that there's a famous theorem that indeed says that this scheme is indeed a universal approximator for any distribution that you can think of. And if there's any mathematicians on the line, I know I'm being a little cavalier here, but roughly speaking, it says if you have any distribution of classifications of outputs that you're wanting to model, that there does indeed exist a neural network with enough hidden units to approximate it. There's some problems with it. It turns out that it's often hard to optimize the models if all you're doing is adding hidden units. So there's another dimension that we can move in. We can add hidden layers. Adding hidden layers basically means that what was an output layer now becomes an input to the previous or to the next set of hidden units, hidden neurons. And so what was a matrix vector plus vector gives you, and then of course you apply your nonlinear function and gives you an output. that becomes your next vector to the next layer with another matrix multiplication and so forth. And so these things stack on top of each other. Okay, so you could use a loss function just like what we did earlier. Okay, so we've basically talked about all these building blocks. A loss function, we were just using a variation on root mean squared earlier. Gradient descent, we've talked about that. Now, before, gradient descent was a derivative on a very simple linear function. Now we have a big nested composition of functions. And the buzzword you'll see in the literature is backpropagation, is the buzzword about how do you apply these derivatives, or how do you find these gradients on one of these deep nested nested functions. Backpropagation is just chain rule. So whenever you take a derivative of this big long nested piece, you eventually have to go all the way into the middle of it, take the derivative of that, multiply it, then take the derivative of the full next thing, pop it out, multiply it, and so forth. I decided not to give a calculus lecture here, so I'm just going to verbally say that. Well, but the point there is that's actually what all these AI machine learning packages are doing for us. They have gone and collected all the basic types of layers, in particular neural networks, and programmed in the formulas of how do you walk back this back propagation. And they've tried to do it in optimal ways that loads it onto GPUs and does it, in one big clock cycle and all that type of thing. But they all basically do the same. They all basically do chain rule on a big composition of functions. So yes, loss function, gradient descent, backpropagation is part of gradient descent. The optimizer is the particular formula for the way we update the parameters. An activation function is just some nonlinear function that's buried in our nested model. Okay, great. Any questions? I've given these kinds of talks so many times. I actually don't know where people may or may not be getting lost anymore.
I have a quick question regarding coding. So I'm not sure if it's something with Jupyter or HAL, but the first cell, it gives me the error that the module NumPy is not found. I'm not sure if I need to pip install it.
No, not yet. No. So over here, it tells you what kernel you're running. And the kernel that you should use is under the kernel menu, change kernels, come all the way down to Conda env WMLCE 1.7.
I see. Okay, thank you.
Just to reiterate, the pip installing this is running on HAL. Right. Yes, it's displayed on a web page on your notebook, on your laptop, or wherever you're sitting right now. So pip installing something, you'd have to come over here and interact with a multi-user environment. So the HAL team has done their best to put together as many useful packages as possible and wrapped it all into this Conda environment. There are other ways of managing packages, but this is the way that the HAL team has chosen to do this. So yeah, just to reiterate, if you're kind of coding, cruising along coding, and you bump into a package you can't find or can't get, perhaps just come through and peruse what's going on over here. Of course, reach out to the HAL team and all that type of thing. All right, good question. Anything else? Okay. Neural networks. Okay, convolutions. So neural networks were one of the probably one of the earlier AI type models that people studied back in the 80s. They've still lingered around. They have that great universal approximator property. They're probably not going away. However, also back in the 80s, there was some early work with mixing convolutions with neural networks. It really didn't take off though until 2010s, around 2014 or so. So what is a convolution? If any of you have studied signal processing, these convolutions are indeed the same thing as a convolution you know about in signal processing. They're higher dimensional and they're discretized. So a convolution happens by first choosing a signal, or you could think of an image. Here's a oversimplification of a raster. Instead of displaying a pretty picture here, we display the numerical value of the raster. Zeros, presumably white cells, ones, presumably black. And so we have this input piece of data that could be interpreted as an image. And then you have a kernel. Typically, kernels are smaller. In this case, it's a 3x3 kernel. And a convolution is a process by which you combine these two things to produce another raster, another array, another set of organized set of numbers. And that process involves taking your kernel and sliding it across your input image. And so in this in this demonstration here, we've slid the kernel over to the I guess you'd call that the fourth position or third, depending on how you're counting. And in the fourth position over, you take each item, multiply it by the item in your kernel. So 1 times 1, 0 times 0, 0 times 1, 1 times 0, 1 times 1, 0 times, and so forth. And you get ones and zeros all through there. And then you add it all up to produce 4. So that's the process of convolution. You take your kernel to some corresponding swath in your image. You perform this point-wise multiplication and then add it all up. And then that is your new pixel, your new value for the array. And then you slide your kernel over and you do it for the next pixel, and you slide your kernel down and over and you do it for another. The step of the kernel is called the stride. You don't have to do it one at a time. You could do it 2 at a time if you wanted to. You don't have to do a 3x3 kernel. You could do a 4x4 or a 6x6. It turns out 3x3s are common. And there's a reason for that. I might get on my soapbox and explain that later. So that's the process of convolution. Well, that seems like kind of an exotic formula. Who cares? There are lots of abstract reasons, but the heuristic reasons, let me make sure my cells are all updated here. But the heuristic reasons, let's actually do this on a piece of a real image here. So here we have an image, what looks like a staircase. It's a grayscale image, that's fine. There are people in it. There's a sky behind it. Maybe it's a cloudy, no, it's sunny. To me, that looks like it's sunny. You have lots of sharp lines. You have a little bit of organic lines in here too. Some places, lots of contrast, some places not as much contrast. So this image has a lot of photographically interesting features going on. You might take this picture for an art class. Here for demonstration purposes, we coded up a simple convolution. Honestly, we coded up a simple convolution. This is another choice where, for demonstration purposes, so you can see all the nuts and bolts of how this works. Here it is in front of you. But this is also what those machine learning packages are doing for you. They've coded this up for you and have optimized it for whatever architecture you're running on, GPUs, CPUs, whatever. But indeed, all it is in this simplified version of it, is it's two nested loops that's scanning this kernel over and then down, and then over and then down, and then over and then down. It might be down and then over. I always get my indices flipped around. So let's run that. So I define the function. The filter we're choosing is this negative 1, negative 2, negative 1, 0, 0, 0, 1, 2, 1. There's a description of it over here. We'll get to that in a second. Define the filter, and we apply it. Uh-oh. Oh, I think this does happen. One more time. All right, there was a trick to get matplotlib to display correctly. I kept it in here. I never remember the exact. Come on. The exact this guy. That's what I was looking for. Where is it? Come on. Whoops, that's not what I wanted to do. There. There we go. So here's our original input image, and then this is the result. Presumably, it's probably about 2 pixels smaller, maybe 1. That's always an off by 1 error that I make. But it's transformed this image from something that looks pretty to something that still might look pretty to you. I don't know, but is certainly different. And to our human eyes, you might see that it actually kind of highlights some things that indeed are syntactically important. Right, this bar here really came out where it hit everything else in the background. All the railings here really popped out. Over here, it's a little bit hard to see them, but now we have a striking representation of them. So convolutions can be used to transform your input data to try to highlight and bring out interesting features. It turns out this technique is well known in image processing. This is called a bottom Sobolev. Abstractly, this is basically like taking a derivative in of an image moving from left to right. So classically, computer vision and image experts have discovered some of these convolutions do useful things. Let's try one of the other ones. Different, again, called the right Sobolev, or horizontal, or I guess it's horizontal edge detection. Let's do an outline. So there you go. I kind of wish we could do a sharpen. Let's do an emboss. Let's see what that does. Okay. Actually, can I make this bigger? No, darn. So yeah, emboss just kind of brings out more sharper details. Okay, great. So now we have two ingredients. We have neural networks, and we have these convolutions. And with those, you can combine these together and indeed start building models to indeed try to fit your data. So some of the most common ways of starting computer vision ML models is just starting to stack these convolutions. So your input layer is an image. It has however many channels you want, or that the image came with. In our case, it was 1. You can do 3. The first convolutional layer is basically saying, hey, there's a kernel. That's all the convolutional layer is in terms of raw data, is it's a kernel. So you can tell how big of a kernel you want it to be. Do you want it to be 3 by 3 or 4 by 4 or so forth? But you can also, with all these ML packages, you can also choose how many kernels. So it will, in one big blast, do some 64 kernels all at once. And we'll see a demonstration of that in a little bit. So these convolutions get stacked together. And each one you choose how big you want your kernel to be and how many of them you want them to be. But eventually, at the very end, you flatten your image just like what we did up above, and you hit it with a neural network. And this is where the final classification comes out. Okay, cool. Any questions so far? Okay. Now, one more ingredient we're going to use in the upcoming demonstration is max pooling. Nothing magical about max pooling. There's actually no weights to be trained here. There's no weights to be trained here in all the common implementations of this thing. Max pooling is exactly what it sounds like. Is you look at several pixels and you take the max value. Why would anybody ever think to do this? We're going to see some evidence in a little bit that makes it a little more clear why somebody would do it. We've seen it a little bit here. If we go back to, maybe if we go back to, come on, there it goes. Back to our filters and look at and look at the left or right Sobolev. There, if you were just to randomly choose a kernel, most of them will actually give you something very nondescript. It turns out that one of the things these convolutions are trying to do is get rid of all the superfluous things you don't care about. Right? Just from this transformation here, you get these big swaths of black with only little highlights in here. So that's part of the motivation why max pooling winds up being so a useful thing to add to your model. Is you're trying to take this high dimensional image data and reduce it down to something, reduce it down to something smaller that can that can be classified. Okay. So that is the intro. There's a lot of cute little things you can play with in here. I should have coded it up better. Like up here with the scatter plot, you can actually step through and watch how the line changes. Down here with the convolution, you can modify this and do and do bigger filters if you wanted to, and go and muck around with these values and see what kind of pretty art you can generate. So there you go. So that's the intro. The next thing we're going to do is let's do a semi-real problem. I'm gonna go ahead and shut my. No, I'm not going to shut it down. I think I'd come back to it and talk about it a little more later. So a surrogate problem to build up to be a little more sophisticated than just linear regressions and convolutions. We're going to study a data set called MNIST. MNIST, NIST, National Institute for Standards, and I'm blanking on the last one. Whoops. Where did it go? So I'm going to open the MNIST. Uh-oh. Still says my interactive session is, uh-oh. Technology, thank you. Thank you, Bill. Vlad, I think there's a problem.
Yeah, Jan was just telling me that we have something like 40 open sessions in Open on Demand, and I think that's kind of stretching it a bit.
Okay. So should I just pause? Well, that's sorted out.
Yeah.
There's 40.
Well, I think there are other users in the system, so.
Oops. NIST, National Institute of Standards and Technology. So while we're waiting for things to come back on, I'll soapbox a little bit. Right. So this MNIST data set is a data set that is NIST one of NIST's machine or AI benchmarks. And it is a data set of handwritten Arabic numerals. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. It's a big data set that they collected of people doing this, of drawing it down. And once I can get a display up there. But this is, in terms of, kind of a federal overlord, the closest thing that you can really get to 100% official benchmarking data set. This is something that you can use if you have some harebrained idea about designing a model to do whatever. This is probably the data set you want to monkey around with first. It's small, lightweight, and there's plenty of interesting things that you can discover with it, even though it is very very simple. Oh, are we back? No, we're even worse dead.
Can you try it? Because that seemed to work for me.
Okay, let me. This is me, my interactive sessions. Okay, well, we'll pop over here to all right. So it does look like Firefox seems to be working. I'm going to bring this guy up just so I can pop back over to it. All right, so now let's go through the process of putting a model together and studying an MNIST data set. So here we have our initial cells. This thing here is more for when you go and try to play with these kind of things on your own using GPUs. This is the environment variable that, depending on the particular version of packages installed, you have to call to make sure that the GPUs are visible to whatever executing process there is running. So if you have more questions about this, I can answer them after we get through all of this. But this is not the focus of what we're doing today. All right. So cell 1 just ran. Here I'm just importing some utilities, setting random seed so that I kind of know what to expect coming later. I input Keras and just for our own sake, own sanity, display the version. And here we are with the data set. So, like I said, MNIST is kind of probably one of the most standard benchmarking data sets that you can play with, and all of these AI packages are going to provide it for you. So TensorFlow Keras dataset, import MNIST. To get categorical, we're also going to want to use this to categorical function. And this is the opportunity I'm going to use to really emphasize what does the output of these models actually look like, right? I've kind of mentioned things about regression and classifying things and whatnot. Here we're actually going to see what that data actually is. All right, so did I run this one yet? Oh, it didn't display. Whoops. Let's see, how do I want to save this though? So here we have our test labels. So here we import all the data. We do a reshape. It turns out that the raw data is going to be a 28 by 28 image. There's 60,000 of these for the training set. And for the way that TensorFlow constructs the data, the data structures to actually perform things like matrix vector multiplication in the neural network or the convolution, it wants a channel dimension there, whether it be 1 or 3 or 27. We're going to deal with just grayscale images, so we just need one. One step that always slips my mind, however shouldn't, is normalizing your input data. That's what this line is for. It turns out that these are are the raw data was some size of integer, but we want to make sure that their float 32s normalize between 0 and 1. If you think back to your calculus course about gradient descent, gradient descent is about traversing a lost landscape. Think about it as a whole bunch of hills, valleys, hills and valleys. The actual model itself is going to provide a lot of interesting topography going on that gradient descent is going to be searching through. It doesn't need help from the size of the value size of the input data. So it is often best practice to normalize that input data down to between 0 and 1. If it's too big, often your gradients overflow. They just get bigger and bigger and bigger, and they never find an optimal minimum. So whenever people are designing models, they are often designing them expecting that the input data is normalized in order for the optimization process to work nicely. Okay, and so we do that for a test set, and we run two categorical. Actually, that was a little bit disappointing. Let's comment this out real quick. So the way the labels came from the raw data set here is just a list of numbers. I mean, I verbally told you haven't seen it yet, but these are the labels: 7, 2, 1. Very precise, discrete values. And our task is to classify these. So we represent them in what's called a one-hot encoding. It turns out that Kiris calls it two-categorical, which takes that digits, that number 7, and creates, and since there's 10 classifications, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, puts a 1 in the position of the classification it represents. And that's what two categorical means. It is commonly called a one-hot encoding. So you took your scalar and you expanded it. That's why these diagrams over here always had several. Oh, is there a better one down here? No. Oh, yeah. These diagrams down here always had a lot of outputs. These outputs represent the category that they're trying to predict. Okay, enough blah, blah. Let's look at some pretty pictures here. So what do these actually look like? These 28 by 28 rasters, they look like handwritten digits, 5 with the label 5, right? This piece of data is a 28 by 28 raster that happens to, that us as humans happen to interpret as a handwritten 5. Its label is a numerical 5, or after two categorical, it's a 10-dimensional vector where the 5th position in here is 1. And you have 0, 0, 4, 1, 9, and so forth. Some of them are pretty. I could never draw my 9s like that. Some of them are ugly. This is more like what I draw my 9s like. Fives are horrible. But we're going to build a model that can look at this raster and return the numerical representation. The numerical representation. Yeah, I ran that. Okay, here we go. And so here it is. Or here's a zoomed in version of this after it's been normalized. So 0 is where it's black, 0.99 where it's white, and everything in between. All right, so that's the data. Now let's look at the model. So from the intro discussion, if you got nothing else out of this, I hope that you got that the ingredients that we have here can be layered, can be stacked. So you can put one hidden layer after another. So you can put one convolution after another. The way the vast majority of these machine learning libraries work is indeed list out the sequence of layers that you want that you want to build your model. That was the great abstraction, studying layers that generically fit together. So in Keras, we say hey, of all your types of models, the big classification of category of models that we want to use we'll call sequential. I personally have a beef with them calling it that, but you can ask me what that is after class, and and I'll tell you. And to that model, let's add the layers. So a two-dimensional convolution that's going to have 32 kernels. You can think of this as 30, it's going to expand the input into 32 channels. But there are 32 independent kernels, and they're going to be 3 by 3. The activation function we use is called a rectified linear unit. And here we have to tell a little bit about the input data. Remember when we looked at some of these diagrams over here, this matrix here was sized because this diagram said there are 3 inputs and 4 outputs. And so because this is the very first layer, you have to give it a clue what to look for, so it can initialize this matrix properly. Or, well, yeah. We add a max pooling layer, a 2 by 2. For kicks and grins, we add a another convolution. We spice it up a bit with 64 kernels, each of them 3 by 3. Another max pooling. And lastly, a 2D convolution. All right, so that defined it. What does this thing look like? Ooh. Huh, okay. So model summary confirms what we set up here. Indeed, there's a 2D convolution, max pooling, 2D, max pool, 2D. These are the shapes of the arrays that actually make up the output. And this is how many parameters are there. Let's see, yeah. So let's see, 3 times 3 times 32, 288. Oh, plus the bias, whatever the bias term was. So at least a close order of magnitude plus bias. Max pooling has no parameters. There's nothing there that we're trying to train. It's just a generic operation. And so the summary gives us an idea about how big this thing has gotten. Okay. So now after we stack all these max pools and convolutions together, this thing is still going to look like some version of this here. It might be super grainy. We'll see some examples of this later. It might be super grainy and ugly, but it's still going to be some version of this. So we need to take some version of this and convert it into our final thing that we use to predict. And so we flatten. We take that raster and flatten it in a big long vector. Keras and TensorFlow call neural networks dense layers. They're dense because all the hidden pieces are all connected to each other. They're densely connected. And we're going to have 64 hidden units. It turns out that last predicting layer is just a variation on a dense layer, but instead of a rectified linear unit activation function, we use a softmax. Softmaxes are interesting functions in their own right. I encourage you to go Google it and look at the Wikipedia entry for them. They're basically a way of normalizing everything. So, so the output layer looks like a probability distribution. So now, oh, did I run it? Yeah, I ran it. Good. While I'm talking here, I'm forgetting which cells I'm running and which ones I'm not. Sorry, guys. Okay. So bam, bam, compile and train. I'm going to get this going because the training is actually taking a little bit. So we're going to get that going while I talk about this. Okay, so we told TensorFlow or Keras what the actual architecture of the model was. Because we're using ingredients that are super generic in the best ways possible, it was just a sequential model. But we still have to tell it, how do we measure how good the model is? And what is the particular formula or scheme that we want to use to update the parameters? And so that's what optimize and loss does for us. So, so the optimizer, RMS prop. Our RMS prop is basically a gradient descent, but with an extra momentum term. I'm not going to go into all the details, but the formula is spelled out down here. So W is that weight matrix that I was showing you in the intro discussion. Alpha is still your learning rate, but the gradient is now combined with this crazy formula going on here. Partial, oh, why did you put that there? Huh. Okay. J happens to be your loss. It turns out in literature, they use everything except L. So the literature that RMS prop was described in, loss was your J. And remember, you're taking the partial derivative with respect to the, with respect to the weights, W. Not with respect to the data, with respect to the weights. The data is fixed. The data was chosen. It's those 60,000 input images. Done, fixed, static. The thing that's changing are the weights of the model. It's the values of the kernel. It's the matrices in the neural networks. So RMS prop is this extra business here. And this roughly represents momentum. You know, in models, there's no mass, so you take that with a grain of salt. It's using an acceleration. I forgot if it was RMS prop or atom optimizer. One of them was actually derived for a Coursera course, and the lecturer did it just to show that there isn't any special magic going on here. Deriving these formulas are just variations, or just improvements on gradient descent. And look, here's a random one that he decided to use, and it wound up working really well, and wound up publishing or soft publishing the paper on it. And I think it might have been RMS prop, or it was Adagrad. Oh, it might have been Adagrad. But there's a whole family of these things. Okay, so that's your optimizer. In the previous intro, it was just generic gradient descent. Nobody uses gradient descent by itself. In Keras, we're using RMS prop. Okay. The loss function is categorical cross entropy. Oh, geez, what is this thing? This is its formula. You take the, let's see, let me recall. P is the predicted probability. So P is what your model is predicting, and Y is what your training set was. Take the log of what your model is predicting, and you multiply it by the value of your training set. You say, well, geez, that's kind of crazy. Without going into too much detail, it turns out that, you know, whenever you're dealing with classic statistics, a lot of your distributions are exponentials, right? The Gaussian is e to the negative x squared. Yeah. And so it turns out that working in log space it gives you, working in log space takes what was this exponential problem and turns it more into a linear problem. Yes, I know I said x squared, but you know, for argument's sake, it's taking these curve fitting problems that you would have had to compute an exponential and turns it into a log problem, which incidentally becomes linear. That's sort of where this formula comes from. So we could have used the loss function from the intro, but it turns out that whenever you're trying to model something that's drawn from an some actual distribution, we don't know what the distribution is, the convergence properties of categorical cross entropy wind up being better than using a naive thing like root mean squared. So whenever you're dealing with categorical type optimization, it is very, very common to use cross entropy. Whenever you're dealing with regression, it's very common to use root mean squared. And the reasons happen to have to do with the way the formulas for common distributions are. To learn more about that, there are there's a link here. Goes to your CS 231 class to talk more about it if you're interested. Okay, so what is this training loop actually doing? So clears the gradients of all optimized variables. So initially, it randomly initializes everything. It computes a forward pass, so it expands that, it pushes the data through the model to get a predicted output. That predicted output is used to calculate a loss. That loss function, remember, this this loss function up here, we're performing a gradient on it. This P encodes the big formula that is your model. So you're pushing a gradient down this big complicated formula, whatever this came out to be. Fortunately, all meaningful loss functions are going to be a big long sum. So the gradient gets distributed across the sum, and it hits each one of these items individually. And each one of these items individually gets this backward pass gradient, the back propagation that we talked about earlier. Back propagation is what gives you your actual gradient. Whoops. Oh crap! Don't do that. Okay, good. I was worried I was going to restart the fit. What was I saying? Back propagation is what gives you the gradient. The gradient goes into whatever your optimization formula is, and updates your weights. Updates the kernel or the convolution kernels. It updates the transition matrices in your neural networks and whatever exotic ingredients you threw at your model. And it does this over and over and over again, just like in the linear regression. It chose a bad line and it updated the weights until it was a good line. Yeah. And so, yeah, Keras has a method called fit. Fit pushes the data, does this loop over and over and over again. You can observe that the loss improves. The accuracy improves. Loss and accuracy are strongly correlated, identically, maybe. Okay, I'm going to take a brief breath. Are there any questions? We've just done a lot. We introduced a real model, what real optimizers and real loss functions look like, and we trained a model. Questions?
Looks like there's no questions so far. So far, so good.
There'll be a test? No, there won't be. I stopped teaching because I hated grading. I loved working with students, hated grading. Okay. So now we have our trained model. Bam, bam. Keras gives us a method called evaluate. We can just evaluate all the test images. Oh, right. So here's the point. This training happened on training images. The full data set was partitioned into things that the model would see during training, and a few images left over that the model would not see. It was not exposed to gradient descent. It was not exposed to the optimization. And so in this cell that I have highlighted here, that's what we've evaluated. And lo and behold, the accuracy, the loss and the accuracy are just as good, maybe even a little bit better than the training. Or in other words, this model generalized very, very well. That's the goal. That's the big thing that blows classical methods out of the water, is this ability to generalize, to be able to take in a whole bunch of data, optimize yourself on it, but then take in data that it's never seen before and still perform really friggin' well. That was the surprising thing when neural networks, machine learning, convolutions, and all that started working well. That was the scary thing. I mean, yes, we're only dealing with handwritten digits, but hopefully abstractly you can see how, if you had a set of images of all the people that you've ever met. Oh, yes. Yes, we will get there. I do have time for that. There's a question on the chat. So that's the amazing thing, that this thing generalized well. On this toy problem. But it doesn't necessarily generalize well. Well, in this toy problem, it does. But different classes have different levels of accuracy. For example, this one was able to identify the number 1 really well. But for some reason, the number 9, it had a little bit of hard time with. I don't blame them. For some reason, my handwritten number 9s are awful. Even just looking at this data set, they're basically 2 different ways that you can draw a 9. You can go zoom, or you can go zoom. So this model struggled a little bit with that particular classification. All right, so individually, we can deploy this model and do it just on single images. If somebody, was tapping on their iPad and drew a number, and then you could pick that number up and send it to this model, indeed, it would start to predict pretty well. So a little zump means predicted as a 7. All right, we're running out of time a little bit, so I'm going to speed up. Generators are super important in terms of data management. You want to be moving all your data around with generators, but we're not going to get into that too much. So looking at some more of these digits, this is kind of what we saw above, and our model is doing really well predicting all these things. But even from our accuracy model, calculations up here, they didn't do perfect. Let's go look at some of those. All right, I forget. Let's see. Predicted and labeled. Okay, so on the left is what it predicts. On the right is what it was labeled. So National Institute of Standards and Technology says that this is a 9. Our model says that it's an 8. Rhetorically, what do you guys think? Yeah, it's kind of a 9, but it's a really bad 9, and so forth. A really bad 4. Our model thought it was a 2, though. So even though it was getting some wrong, even us as humans are like, what were these people thinking when they wrote this this number down? So you can't quite blame the model. Okay. Interpretability. This is kind of a super exciting topic these days. We want to look into these models and basically see what they're doing. What does this do for us? Let's see. Off the top of my head, when you're, what it makes sure that these big long formulas, how do we know that this model, all it was doing was maybe is only looking at 5 different pixels around here? And NIST, National Institute for Science and Technology, actually did a really bad job labeling these things. And it just so happens that every 7 has a white pixel right where my cursor is. Maybe the training set was bad in that, and that's actually the way it was classifying. So we want to be able to, after we train our model, we want to get a sense of, is our model actually looking at relevant data and not something coincidental. Okay, so here's a fun animation. I'm pretty sure Saad Khan put this together, but I'd have to go double check that. that animates the actual Rube Goldberg machine that these things are. So we have our raster image. Oh, in this case, it's a 2. If we chose to do this with a neural network, with, by the way, I encourage you to go build just a pure neural network. They're surprisingly good at MNIST data. We included convolutions and all that kind of thing, mostly for pedagogical reasons. So you saw that you can do it. So you go take this raster image and you flatten it out. The inputs here, you'll notice that some of them are hazy, some of them are black, some of them are a little brighter. So from this big, long 784-dimensional vector, what about it makes it special and interesting? Well, that's what these formulas for neural networks are trying to do. They're trying to take all this fuzzy input data and separate it so that it becomes more clear and distinct. So what was just a vague notion of a numeral 1 becomes, in one of these latent spaces, I haven't said that word yet, in one of these layer spaces here, often called a latent space. Remember, these layers here are the result of this matrix vector multiplication, outputting some values. So one way we interpret this is a model is doing well if its later layers indeed have very distinct activations and are not wishy-washy, or not vague, have very distinct signals coming through. That's how that is one way we can interpret a model and say, it did indeed learn something good here. Okay, I need to think about. So I'm getting to projection. Yeah, let's look at that more holistically instead of just this little piece here. All right, that ran. So I'm okay. So what's going on here is, in order to pull out these latent spaces, I have to go build another surrogate model, an embedded model, and pull out a particular layer inside of it. And so with this embedded layer that's pulling out a specific output layer, so not the final output layer, but a specific one, that's what this model code here is doing. I ran it. Building this model also takes the inputs from your previously trained model. So this embedded model is your trained model, but we're siphoning off the second to last layer. Right shape. Yes, good. And what are we displaying here? All right, the second to last model, if you remember, was a dense layer, 64 dimensions. Remember, we added two dense layers. One was the final classifying layer, but one before that was the 64-dimensional. So on the horizontal axis here, there are 64 dimensions. On the vertical axis here, I think we took off 5. Where is it? Or 10. On the vertical axis here, we stack all these outputs and we group them together. So down here, we took all the outputs that represent 9. So a handwritten 9 went into the model, and a 64-dimensional vector came out in the latent space. And this is its heat map. And we stack 10 of these together. So this is 10 different 9s that we push through the model, 10 different 9s here. And we're plotting the heat map of their latent space, of their 64-dimensional latent space. And we indeed, so at least between like 9 here and 8, how are we doing on time? Good. Between 9 and 8, well, 9 lights up these dimensions a lot more distinctly than 8 does. 7 does also. So, how does the model know the difference between 9 and 7? I don't know. Oh, but if we look at these dimensions here, the model lights up these dimensions for 9, but not as strongly for 7. And you know what? 7s and 9s look kind of similar, but the model was still able to separate these things out. The one that fascinated me was 1. One is unique in the sense that it doesn't light much up at all, probably because so many numbers have a spine to it that's kind of like a 1. So then I kind of wonder if the numeral 1, the reason the model can predict a 1 is because it doesn't have any extra little doohickeys on it, for lack of a better word. So yeah, to finish that description, so the vertical axis is our classifications. We group 10 9s, 10 8s together, 10 7s, 10 6s, 10 5s, 10 4s, 3s, 2s, 1s, 0s. And our human interpretation here indeed does look at this and says, oh yeah, 6 lights up strongly in a similar way. All right, but even this is a little bit wishy-washy. I'm not going to get to this tensor board stuff. So this is a little bit wishy-washy. So we take these 64-dimensional vectors. There are many different projection algorithms. There's one called TSNE. I encourage you to go to this tensor board projector, take the output files from this cell and feed them into this. And if you tune it right, indeed, these 64-dimensional vectors can be projected down into 3 dimensions. And the model learned how to take this vague input here, and isolate them in such a way that their projections are distinctly separate. Or in other words, it confidently said, the way it confidently said, the way that it took, it combined all the pixels in the image together and processed it. It's very certain that it was a 1 or a 2 or a 3. So to describe this a little more, if it's not clear, it's projecting that 64-dimensional vector down into 3 dimensions, and it's being colored by its true classification. So the red here is the way all the 3s got projected into the latent space. And the model was so confident of it that it projected it far away from this blue region, which were the 0s, or this gray region, which were the 7s. Okay. Any questions on that? I stuttered through some of that. I just finished my tea. Hope my throat holds out for another 20 minutes here. All right. So that's great. That was the last remaining. So this was an analysis of the last layer. Let's go look at some of the intermediate layers. Ooh. Hope that didn't screw it up. I don't think it will. Remember that this thing is more than just a neural network like what we studied up above. It's a whole bunch of convolutions. And it turns out that these convolutions, I kind of went on this big tirade earlier about, computer vision people discovered good kernels and good good convolution kernels a long time ago. It's a little miraculous that that training this simple toy model, it's discovering an edge detection too, something very similar to the Sobolev. Indeed, a 2 here, after it's passed through a convolution, after it's passed through the trained convolution, identifies that, oh, this piece under here, this edge on the bottom is important, this edge vertically is important, and this edge here is important. So this is the evidence that we look to say that, all right, whatever the specific details this model is doing, it's at very least looking at this part of the input data, this part of the input data, and this part of the input data. So it's not just doing something silly and coincidental, like only look at 1 or maybe 5 random pixels. It is looking at pixels that, that are syntactically significant. Oh, I didn't prep that. Neuroscience and all that kind of thing. There are neuroscience models of the way people interpret their scenes around them. And it turns out, I forgot to pull those papers together. It turns out that no, when we look and interpret things around our environment, edges are the first thing we detect. And there are neurological studies showing that brains light up in a particular way, and the way we respond to stimuli. Indeed, these are the kinds of things our brains are looking for. And this particular trained model highlighted it. All right, let's see, that was, right, this is the first layer. This is the, this is the 5th kernel, the 5th convolution. Remember, we can stack many convolutions in one layer. Here's the 6th convolution. It's detecting edges also. It's detecting the other ones. Super neat. Bottom and to the right, upper and to the left. Holy crap, that's really neat. All right. Let's see, what do we got here? These are the names of the layers. Now what are we doing? Oh, right. So let's do this a little more holistically. So these are all 64 of them. And then here's all 64 of the max pooling. Again, these convolutions really isolate what's important. So the max pooling just brings what's important forward. And so convolution, max pooling, 64, presumably there's 64 convolutions in here. And as we move through, it's looking less and less like a 2. Again, the model is trying to find ways of taking the important features in the input and separating them so that they're very distinct and isolated. And here, by this point, you can't interpret, you as the human don't see any 2s anymore. Okay, so that's just looking at the anatomy of the specific details of neural networks and convolutions. We can roll all this stuff together, and it turns out that the important feature in all this is looking at the gradients of all things. There's a couple different papers out there. I'm just going to run a whole bunch of stuff there. Okay. that help with interpretability of models. The way these things kind of sit on a spectrum, some of them study very specific features of of your model. They study very specifically neural networks, or they study very specifically convolutions. That's what we just did. We studied specifically how do neural networks express interesting features, and how do convolutions express interesting features. And then there are papers that try to understand what the model is doing, treating the model as a complete black box, not looking at what the formulas are inside, but just looking at the inputs and outputs. Then there are papers that are somewhere in between. And that's what this grad cam is all about. So this grad cam assumes that you at least know what some details about the parameterization of your model and what the gradients kind of look like. And so this next visualization is kind of splitting the difference. We're not completely treating our model as a black box, but we're not looking at exactly its details either. Running out of time. So these functions here are going to go and extract the gradients from the model, presumably the last gradients that were calculated during the training, and superimpose them for these particular images, and superimpose them for some particular examples. If you want to know more about this, go read this paper. Also, go look at Keras has a good tutorial. The Keras website has a good tutorial on GradCam that will go through more of these details. All right. So here we take one image from our, I think this was from our test set. Yeah, from our test set, and plot it. The image show just plotted in a heat map. This is like what we've been, oh yeah, we've been looking at those a bunch. And then this crap, I already forgot the name of it. This GradCam heat map function takes this image, examines the gradients that were responsible during training. Oh, it's still running. Okay, good. Oh no. I might have, here's how we're going to fix this. Because I'm being a little spastic about how I'm running these cells, the names of these layers got screwed up. So we want conv5. This won't take me long to fix. Conv5. Rerun that, rerun that, rerun that, rerun that. Yes, good. So looking at the gradients that were responsible for training convolution layer 5, unfortunately, I've been running these cells over and over while I'm trying to speak to you. So that's why those names accumulated. And so indeed, it's the pixels that are most responsible for predicting that this is 0. Well, the most responsible one here is down the right-hand side. So for some reason, it's looking down here for a 0 the most. And then it's also checking up here. Or in other words, if this was the feature of the 0 that got changed, this is the thing that would, that's the thing that would knock this input out of the 0 classification. So if you change this region a little bit, and also you might have to change this region a little bit, the model would start to get confused and not know what classification. Or maybe if you did it in a good way, let's see, what could you do to modify this? If we were doing letters, if we took the top off, that would look like a U. So it would go from an O to a U. But for one reason or another, the model decided that looking at this region here and this region here was the thing that made this a 0, and not looking in the middle. Okay. See, superimpose image. So it should have, I think my order of cells are a little mixed up. So it's there. That's what I'm looking for. So indeed, combining all this together, this is what we see again. So when the model is looking to decide if this thing is an O, it is indeed looking around the perimeter. So let's look at this for a few other numbers. 7, 2, 1, another 0, 9, 4, 1, 4. And by and large, it is indeed trying to find, or the parts of the input that are most responsible for its classification result is where somebody is indeed writing. So we have some level of confidence that this model is not finding some weird convoluted logic to decide that this is 0 and this is 1. Indeed, it's looking at where these pieces are. And there. And that's just where these heat maps are. These gradient heat maps are without the superimposed portion. Ooh. How are you guys doing? Anybody still out there?
Yeah.
Yeah, good. So if there's questions, I can answer them. Hopefully, through this process, you've seen how to start up these notebooks, run some basic stuff, and get an idea what the process is of defining a model, running it on your data, and then studying how important that model is. Is it doing the thing you want it to? So with that said, I'm done for today. I can hang out and answer more questions or do whatever we want to do. Thank you.
Okay, Aaron, thank you very much. We really appreciate you taking time to present this tutorial. This is really an insightful way to think about not only how to build models, but also how to understand what they do and why they work. So that's great. These tools are very helpful to interpret the model and to make sure that it actually provides the results you expect. So thank you very much. Okay, so with that, we will conclude today's tutorial. Thank you very much for Aaron, first of all, for presenting it, and everybody for attending it. The recorded version of this tutorial will appear on our website, so it will be visible for others to watch. So thank you. We are done.
Great. Hey, everyone.
Bye.